All right, welcome. So today I am going to go through a little bit of the transistor clarification so that you guys hopefully know enough to do all of the rest of the homework. Quiz homework will be due next day. I'm sorry, I can't talk today for some reason. Tomorrow. And then your quiz will be open starting tomorrow morning and then open until Saturday at noon. Okay? Any questions about that? If you have not done the discussion, do that by tonight. So the transistor clarification that I wanted to go over. Okay. Well, I guess I'll back up. So going back to solving a circuit with a BJT in it in the DC, meaning you just have a DC signal on it. You have three modes. These would be the conditions of the modes. And then we went through this saturation example, and I ended up I'll put on here the solution if you use Wolfram Alpha. I just wanted to point out with Wolfram Alpha, I actually had used like variables I, E, I, C, and then I realized after I put them in that I was being recognized as imaginary. So make sure that your variables are not affecting your equation. So when you type them out, make sure that your input interpretation is what you expect it to be if you're using something like Wolfram Alpha. So also E, I used a capital E and I realized it was interpreting that to mean times 10 to the raised to the power. So I realized that was not going to work either. So you can't use those variables. So do make sure that whatever tool you're using, you don't have errors like that. And so this will give you an exercise to be able to go put your values in and make sure they are the same values as these. So I wrote down what I had put in for the equations and then what the end value results were. So I guess I didn't put here. So B was IB, and this was IC, and D was your IE. Oh, that's interesting. Okay. All right, the H bridge, I wanted to just go back to really quickly. So the idea of the PMOS is that it needs to have a very low input to turn it on. So as far as the condition for saturation, you need saturation is that IC will be less than IB, not IV, for an NPN, and VC is greater than, or maybe I'll put it the other way, VB is less than VC for a PNP. So in saturation, remember that this is going to be 0.2 volts, which puts your VC here as 0.2. So in order for this to turn on, this needs to be less than, let's see, VB needs to be less than VC, which is 0.2. And it also has to have a 0.7 volt drop here. So that needs to be, that's not, wait, it needs to be less than in order for it to turn on. So it actually needs to be really low. So VB is going to be limited by that constraint. So it needs to be almost 0 volts in there. So 0.1, or basically a very, very low value. Then it will turn that on and that will become saturated. And so in order to turn on this one, this needs to be, if this one is on, that means that this one again will be 0.2. Erase that one. And then at 0.2 there, in order for this one to be saturated, you're going to have this to be less than, or let's see, if VC is, VB needs to be greater than 0.7. But typically, in order for them to turn on, this is going to have to be high. So I think that's going to be an easier way to say this. High. So if you're working with 10 volts for VCC, this would need to be close to 10 volts to turn it on. And then this one is going to be low, meaning kind of your 0 value. So these work more with kind of 0 and 1, or 0 and 10 volts. All right, on this one, it asked for okay, so I'm just going to do kind of high and low, which would make this easier. So if this is, and then we'll just talk about them being on or off. And when I'm talking about them being on, we want them to be saturated. So in this case, with, say this one is on, then there's going to be current that pulls here. And remember that the current from this will turn on when it goes out. So this will turn this one on. With these being on, this is feeding current into Q3, which also will go on. And so this one would then have a pathway of the current from here through the motor around, and this one goes through this way. And so these need to be off in order for those to be on. So either those three will be on and the other three off, or you would swap them. Does that make sense how this one is working? Yes? No? Okay. All right, I just wanted to clarify that. And then a clarification as far as the flyback diodes. I had just put 2 in there, but this one actually works the best with 4 diodes. So I just wanted to make sure you did have that configuration. So the flyback diodes actually go in like this. All right, and then one other thing, I mentioned how it goes on and off. There's something called pulse width modulation. As I said, I can't talk today. So with pulse width modulation, you're going to have a time period that it's off and then a time period that is on. The different time frames actually, so what happens when you turn on a motor and then you turn off the motor? Does it instantaneously turn off? No, it takes it a second, right? So you rev it up, and then if you take off power, it just slowly slows down. So to control the speed of this, you can rev it up, go off for a second, let it slow down a little bit, rev it up again a little bit, and then slow down. So that will actually control the speed portion of it, so you can time it correctly to be able to keep that more constant. So it's a very slow transition between them, so it's not like on, off, but it will be able to rev it up to a point where you're like, okay, now I can almost keep it steady by letting it coast a little, let it slow down a little, coast a little bit more, slow down, coast. So it will control the speed of it. So the width of how long it's on helps to control the speed of the motor. So it's related directly to speed. So here you see like 25%, 50%, 75%. So the more it's on, probably the faster it's able to go. So the 75% duty cycle is going to be the fastest one. But it will also save power because you're not all on all of the time, and it's really using that time period in between. So this is one way that you can control it. In a microcontroller such as this was from an Arduino, this analog write is an actual function that you can actually do to control this pulse width modulation, and it's a pin that you have on at least this specific Arduino. All right, so those were just a couple things I wanted to point out about the transistor. Do you guys have any questions? Okay. Oh, and then I went through and solved this. So this one we did with the switch open was that the first one was off, the second one became saturated. I went through all of the examples, but I didn't get time to get to this one, which was when the switch is closed, you have saturation on the first one, and then it's off on the second one. One thing that you can note is when you have the first one saturated, this has to be 0.2 volts, and there's no way for that second transistor to be on. So the guess there, somebody asked me, can you kind of guess? You know, that would be one way to say, well, it really just needs to be off. So the other cases of it saturation and active didn't work. So when this is off, there's going to be zero current here. This is where your motor would actually be placed. Again, this is only assuming one model of just a resistor for the motor. But again, that has usually an inductance and the resistor together. And so when I have the switch closed, I have zero current going to the motor, then my motor's off with the closed, and then it's basically open, or zero, meaning that there is a current flowing in the motor. So the motor would be on, and then the motor would be off. So this is a way, and why we were looking at these circuits was to be able to control, for you guys mostly, is going to be motors. Again, it can be any other mechanical element, but motor is probably relatable to you guys. All right, questions? Yes?
So whenever it's an active mode, we expect IC equals beta IB, right?
Correct.
Okay. I don't know, I guess in that case, I think you might have an incorrect answer on your answer key. Or, yeah, D. Yeah.
On which one?
On D. 18-1D.
Oh, on the homework?
Yeah.
Okay, I didn't create those ones, so I'll have to go look at that one.
I want to make sure I wasn't going crazy here.
Okay, so 18, you said it was 18. Do you mind looking at that, Luca? Thanks. He's going to look at it while we're chatting. All right, other questions? Okay. So exam will be on Tuesday in the Ingman lab. Topics will be, so style is similar to how it's been in the other exams. Topics AC, dB, filters, Bode plots, LC resonance circuits, and diodes. So I had a request to go through all of them, so hopefully we can get to all of them today. All right, and I'm gonna skip this one. Okay, due to time and trying to get through all these, I'm gonna skip you guys interacting as much with the answers. So hopefully those that are willing to can just kind of help give your input as far as what would be the answer. So converting from a volt per volt to dB. How do we convert? Correct. Oh, okay. 20 log of V out over V in. So in this case, it would be 20 log of 17 over 19, so you would get a minus 0.97 dB. All right, what if we were converting backwards? So from dB to volt per volt.
dB, e to the dB over 20. 10, yeah, not e.
Yeah, 10. I knew what you were saying. All right, yes. So any questions on the conversion? Hopefully that's just a straightforward, put that in. Okay, if I have this circuit, how do I find the resonant frequency here? What does the resonant frequency mean, I guess? It's more what I'm asking. Anybody able to take a stab at describing that in your own words?
Is it like a bandpass filter, like where the bandpass filter has its peak? Or
So that would be like describing it on a Bode plot.
okay.
So if I have these elements, just what do you know about the elements that is going to create them to be in resonant frequency? So, and also it gets back to, okay, thinking about the Bode plot, how is that WC determined? So if it's low pass or high pass, that's going to be what you want to think about, because those are easier to think about. How do you determine what that is? Any thoughts?
It's at the point when the capacitor and the inductor are kind of canceling each other out.
Correct. So what happens with that is that you have a root of a system. So that's giving you a critical frequency, and when you only have the two elements, that's going to cancel them out and give you also a 0. So because of that, that is why you're looking at them trying to equal each other out. So yes, so they cancel each other out. So what would be an equivalent circuit?
Wire.
It would just be a wire, correct? So 1 over CS equals SL, or if you want to write it in terms of omega, it would be the same thing. It would be J omega is equal to J omega CL. So you're looking at the component values equaling each other. So I guess it's not component values, but the component terms are equaling each other. C. There we go. So to make that happen, that is when omega C equals what?
Is it 1 over 2 pi squared root of L C?
Is it that one? Thank you. So if it's from the equation itself, it will already be in omega form. If you want it in frequency, you would have to add in
2 pi.
the 2 pi. Okay? So you can convert by the 2 pi. So it would be the frequency in hertz would be omega over that 2 pi. So if I did 1 over 2 pi square root of LC, it would be in hertz. Does that make sense? Yes?
Yeah.
Okay. All right, thanks. All right. Okay, this one I'm going to give you a second to do. So this is a diode question. So assuming that all diodes are equal and that they have that VDO equal 0.7, use the constant voltage drop method. Assume D1 and D2 are both on. And then with the diodes both on, solve for ID1 and V out. And then state if that's a valid assumption or not. Okay, so assume that they're both on first. And those that are interested, oh, maybe not. I don't know what happened to my thing. Oh, there's one. Okay, for this one, if you do want to put ID 1 V naught answers in there. You can do that. Okay, quick side note, checked on homework 18. It was 1D, is that correct? Okay, so IE is 8.2, was it 8.27? Or 8.2, sorry.
Yeah.
8.27, yeah. Okay. So that is an error. The reason it's there is they were actually, the solution is assuming that that there's really no current going into your IB for that problem. So note that answer might be a little bit off from yours, but you'll probably be correct as long as you're using that relationship of beta and IB with IE and IC. All right, so got some answers. Okay, remember again, these are both on.
IB or IB?
IB, sorry, yes. IB is 8.27 milliamps, and IE was like 215 milliamps, yes.
Did you get what power was for that? Because I also got a different answer for power on the question. Was that power correct?
I didn't check the number for power, but those others would be wrong if your IE was approximately 215 milliamps.
I think power was the only other one that didn't agree with it. Like the other answers were right, I think power is wrong too.
Power was wrong on that one too.
It was close, but it was also wrong.
So it depends on what the solution. So remember I was saying you can approximate it by just doing IE times times the voltage there. And so it depends if you're ignoring the contribution from the base one. And so it just depends on what, so the answer is assuming that there's nothing really coming from the base. So it will be a little bit off, but as long as you're close to that number. My philosophy again is get some hand calculations, go use a simulator to get the actual values. They're going to be more accurate than your hand analysis. So as long as it's close, it shouldn't be off by like tens of, like a lot. How?
About 0.01 watts.
It sounds small to me. Was yours off?
Sorry.
No, it's
Was it
okay.
off by 0.01, did you say?
His was off by
So,
point.
yeah.
Okay,
Is there something
that's
like
small.
Rings
Okay.
I put down
I can give-
1.66 and it's like 1.65 or something.
Yeah.
It was 1.67 on the answer, but it's 1.65 for P, so it's
Okay.
like that close.
Very close. You guys are good. Don't stress about it much more than that. Okay? All right, go ahead and turn in your answers. That sounds reasonable. Getting a lot of answers here. Okay. So back to the diode. Okay, these are not the same. So minus 19.3 is correct, but the currents are different. So let's figure out how to do these. So you want to make sure to replace the diode that's on in the same direction. Oh, before I do that, which side is negative on the diode? Okay, for this one it will be the top, correct? It's the line side. And then on the D2, which side's negative? Bottom, correct. All right, so follow the same polarity and then 0.7. And so taking, this is ID1. So here you should be able to just do the drops across each So remember, this is really, you can either do plus to minus of a minus 20 or minus plus of 20 volts. Either one is correct way of saying that. So whichever way you like to draw it. If you do a plus and a plus, then this is going to be plus to minus. So this would be a minus. So my loop would be plus a minus 20 plus 0.7 minus V naught equals 0. Or if that's confusing to you, you can do minus plus minus, and it would be a minus 20 plus 0.7 minus V naught equals 0. They're the same. So both of these will yield that V naught is 20 or minus 20 plus 0.7 or minus 19.3 volts. So note there, we're always trying to take a loop with the most known values as we can. In this case, we know the values in that branch, so we want to take that loop. The other loops, we don't know the currents in them. And so that would be our next step of solving for the currents. In order to solve for ID2, we would need to know the current ID1 and the current pole here. The current here is going to depend on the currents going through each of these. So that gets to be a little bit more complicated. To find ID1, this is going to be plus to minus due to the direction of the defined current direction here. And so I'm going to have a plus, minus, minus, minus. So plus V naught minus ID1 times 5K minus 0.7 minus 10. And we know V naught as minus 19.3, so solving this for ID1, we get a minus 19.3 minus 0.7 minus 10 all over 5K, which is, I think, minus 6. So what is that? 2.3. So from this answer alone, what does this mean? It's what? Yes.
Oh, I just have a question. So I guess when we're finding V naught first, why don't we have anything to do with the current and the resistor 5K? Is it just because we're taking like 0 or ground out of V naught or something? Making a loop that way?
So the pathway here went from ground through V naught, through the resistor, through this power source.
Oh, okay. What was the path like before? Like when we first found V naught, I guess below.
So that one went from ground through the source there,
Oh.
back to ground.
Okay. How do you know that? V naught, I guess ground is over there. Is it where?
So whenever it's a node on a wire, that means like I've taken my red wire from my multimeter, I stick it in the circuit there, and I have to connect it to some reference to be able to read it. That creates the connection to ground.
Oh, sounds good. Thank you.
So hopefully that visually
Yeah.
makes more sense to you. So that is something you have to kind of understand, is even though it's just labeled as a wire there, it's in reference always to ground due to, we're really referring to a multimeter being measured there.
Oh, sounds good. Thank you.
So you have to have that ground connection. All right, other questions? Okay, so that's a minus 6 milliamps. What does this mean?
No current through the diode.
Okay, so the diode has to be off. So, or it's basically not on and the other one on at the same time. So you don't know, you have to make a new guess and go through. So this means it's not valid. So not a valid assumption. And then I would guess, knowing that that came back as negative, well, let me see if it's off next time. And then go through the analysis with it on and off and see if that met the check there. All right, questions on diode circuits? All right, let's jump to Bode plots. All right, so Bode plots. First step of a Bode plot. Standard form, thank you. Okay, how do we get this into standard form? It's what? Is the top part in standard form? Yep, okay. So that part is in standard form. What about this quantity? Is that standard? I saw some people, yes, correct. What about the second piece here? Is that standard form? No. So what do we want it, some number s plus 1 is the standard form. So we need to get that plus 1. So need to bring out the 1k in order to do that. So if I bring out the 1k, this ends up being an equivalent. If I multiply the 1k in, that becomes the s and then plus 1k. So this is going to cancel out, and I'll have 100s over s plus 1, s over 1k plus 1. So what does this mean as far as poles and zeros? Okay, correct. So there is a 0 at 0 or 0 at the origin. That means the same thing. What poles do I have?
Pole at 1, pole at 1K.
It will be negative as far as the root, but remember the negative just means inversion, means more of a phase shift. So if I have a positive, I'm getting out a negative, or how much am I in there? So it's more of a phase change. So we're looking at only the magnitudes of these. So if I was to draw it on a imaginary plane, these locations for the poles, you draw them and you're like, okay, this is a 0, a 0 at the origin, and then I have a pole which we mark as an x at -1 and at -1k on this. And because they're on the real plane, they're not complex. So we haven't gone into complex, but that's another thing you'll talk about in control theory if you go take the control theory class. So what this means is that we have a stable system because all of these are on the left side graph. It means we have negatives and they're going to be stable. So I haven't talked about phase. Phase will go into that stability portion of it. It is important, but I just kind of want you to look at the magnitude for this class. All right, so pole at 1 and at 1k. Again, yes, they are negative, but that we only care about the magnitude location of them. So what do these mean? What does a 0 mean? It's going to be a slope, correct? And it's going up or down, correct? So it'll be a 20 dB slope. And what happens with the effects at 1 and 1K? -20 dB per decade. And 1 and 1K are in what units?
Radians per second.
Thank you, yes. Radians per second. And what about this 100 over, I forgot to write the 1K in there. Or no, I didn't. I crossed it out. So what about this 100? What does this 100 unit mean? Or what is the unit? Anybody remember? It's dimensionless because we're volts over volts, or V out over VN. So I gave it away. We're in volts per volt. And so we need to convert that to dB in order to find the point on the graph. So because we have a slope going through, we need to figure out one point that it will intersect on the graph before we can then just draw the rest of it easily. So we know down here we have at 1 and at 1K. These are going to be radians per second. And in order to get dB over here, we need to convert. So we're going to have, unfortunately, we can't use 1. So we're going to use something lower than 1. So we need to know kind of a decade before, at 0.1, what that value is. So at omega equals 0.1, we can take the square root of 0.1 squared plus 1 squared times the square root of 0.1 over 1K squared plus 1. And that will give us very close to 100. So 99.5, and then we take 20 log of that, and that will be approximately 40 dB. So 40 dB, if I pick a point here, I call this 40 dB. What value will it be at 1? Actually, I'm going to move this up. Thank you, 60, correct? So you just add it 1 decade, then it will be. So here at 1, it will be 60. And then what happens at 1? Okay, so we drop by 20, but we've been increasing by 20, right? So what happens? Correct, it's going to go flat. And then there won't be a change until we reach the next one. So this was, go back. So this was increasing at 20 dB per decade. And then this had a subtraction off of that slope of minus 20 dB per decade. And then here we're going to go down at a rate of 20 dB per decade due to the second pole. So this is going to decrease by 20 dB per decade. So, questions on this? Yes?
Where did you get the plus and minus 20 from?
So this is the current rate from here. And then this is the rate from the change. So right at 1, I was coming up by 20, and then I add on the change of rate at that point, which is the minus 20.
But how how did you know it was 20? Like the number 20, where did 20 come from?
Oh, the rate of 20 and minus 20? So if you were to actually put this in, say you only had one pole or 1 0, and you had 1 over s plus 1. You'll see at 1 that after that it will just continue to change at that rate of 20 if you just put in the numbers based on the log. So you're doing them in dB. So if I put in my calculator at 1.5 and see the number, it's going to be a little bit more increased. At 2, it will be a little bit more increased. And so over a decade, you will observe that it's a rate of 20 dB per decade change.
For any of these problems?
For every,
Oh.
yeah. So anytime you have a polar 0, that is the magnitude effect it gives. And it just continues on that way until you get to another change.
Is it the 20 in front of the log? So, or no?
So yes, it's because it works out mathematically based on the log that it ends up being a linear increase of that over a decade. It's an exponential in the volt per volt. But it ends up being a nice linear line as far as a change each time. All right, any other questions? Okay. All right, so there was some questions here. Using the approximation method, at the value at omega equals 0.1, we found was 40 dB. The 0 frequency for this circuit is 1 at the origin or at 0. And then this was 1 and 1K, and then they were units of radians per second. So the slope of the magnitude graph from 0.1 to 1 is what? So the slope of this from 0.1 to 1, positive 20 dB per decade. And the slope of the magnitude graph from omega 1 to 1,000 is what? 0, thank you. And the slope of the magnitude graph after omega is 1,000 radians per second. Correct, negative 20. All right, questions? All right, at 1,000, what is the actual critical frequency? 3 dB below, correct. So it will actually be here. And it's going to be 60 minus 3 is 57 dB. Okay. Any other questions? Okay. All right, what is this what kind of filter is this? Zoom in. There we go. Okay, good job. So bandpass. What is the resonant frequency here?
100.
It's here, right? And 10 raised to the 1 is 10, correct. I can tell that was... Okay, 10 radians per second is our resonant frequency. Is this a high or low Q?
Low. You want a high
Correct.
Q that it would converge closer, right?
Correct, yep. So if it was high Q, you would say like, oh, this would be
It's like, yeah.
way better.
And then it's the inches for,
High Q. Correct. So high Q in cases of band pass and band reject means that it's very limited and very sharp. So this would be a high Q on that one. All right, good job. Okay, that's all I have. we have time for more. So what other questions do you guys have? Or what kind of type of question? I can pull up another one. Yes,
I guess for me, like more diode stuff.
diode? Okay, let me grab another diode. This might be easier. So I was able to get together, started some practice problems, so you can also pull more practice from there, and they should have all solutions. Let's see. No. Sorry. Might get a different. Oh no, it's not letting me. Sorry. I was trying to do it on there so it would be quicker, but it's making me log in. All right, so go ahead and work on this one. Okay, note here that this, no wait, sorry, you're not here. There we go. So note here that this current source is forcing current going the other way or opposite what the diode is, and that's, even though if there's a voltage drop there, it's still forcing current going backwards into it. Which is gonna happen or not happen? Not happen. Okay. So if you weren't told, you would have to say like this is gonna be off. Okay. But you are told to assume that they're both off. So in this case, assume both are off and then solve and verify that they are off. And in the case where you actually are forcing with a current source, you are going to say that that is forcing this to be off. Okay, so with the diode, you're making an assumption. If it's on, then you need to check it just like we were doing with the BJTs. If it's off, then you need to do a check after you've solved the circuit. So if you assume on, what do? You replace it with what? Correct. The voltage source of whatever it says or assume 0.7. And then if it's off, what do? Correct, with an open. So either case, you're going to redraw the circuit, and then once you've solved that circuit, you need to do checks. So if it's on, you're going to check what? So if it's on, you replaced it with 0.7 volt voltage drop, and then you check what? Correct. You check that the current going through it is greater than 0. The current you need to make sure is going in the same direction as the polarity of the diode direction. So when you redraw it, make sure you keep the polarity based on the polarity in the circuit. So this had a plus to minus. This is plus to minus. So remember, minus is always on the the line side. All right, if it is 0, or if it's greater than 0, then you're like, yes, great, that was my correct assumption. If it's negative, like our last case, you would say, no, that was an incorrect assumption. All right, if it's off, you're going to check what?
Voltage across it's less than 0.7.
Correct. So you're just making sure that the voltage across it isn't enough to turn it on. If you do find that VD is greater than 0.7, then again, that will be a wrong assumption that it's off. So looking at this, I labeled the polarities as I redrew them. I assumed that they were both off, because that was what I was told to do. So I'm both off. And so you leave them open. If they're both off and this circuit, what current's flowing through here?
Also 0.
Correct, it's going to be 0 because it's a floating connection. So VO will be what? So I don't know, VD1 and VD2 aren't 0.7 here because they're open. So I don't replace them with the voltage source. So I have to find a pathway from V0 to ground. And in this case, there's only going to be one pathway through there. And again, whenever it's a node on a wire, it means that you're also referring to ground. So that's how you get your loop. So in this case, this will be plus to minus, kind of referred to ground. And up here, wherever you see a arrow or a dot, that means that it is that voltage. Even though it's not drawn, it's implied that you understand that that means it's going a voltage source from that point to ground. So that will be a connection back to ground. So this loop, I can do either direction from the bottom up or this way. I'm just going to go here, so I'm going to go, this will be 10 minus 0 minus 1.3 minus V0 equals 0. So V0 will be 8.7 volts, 9, 10. Yeah. So V0 is 8.7 volts. So what will VD1 be? So a voltage difference means that I put the red probe from my multimeter on the plus side and the negative probe of the multimeter on this side, which means it's going to take the plus side first and compare it to the other side. So that's going to actually be V naught minus this side, which is a minus 10. So it will be 8.7 plus 10, which will be 18.7. What does that mean? Is it off? No. So that's what that means. Not off. All right, on the second one, what is VD2 going to be? Is this a little confusing? Yeah. So there's actually current flowing in here, but it's also an open circuit. So you're like, how does that flow? It's because the current source, the way you make them is actually transistors, and then they are connected to voltage sources, so you can actually get current flowing through the current source to ground and to plus. So let's ignore that for now and just say that unsure, but we also know that this is fixed current, so it has to go and keep that one off. I won't give this to you on an exam. All right, questions? Yes?
I guess like, how would you draw that negative 10 volts as like a battery next to ground?
Negative,
I guess like the down arrow.
okay.
It says negative 10 volts.
So you could draw it two ways. At that point, you can just connect it to a plus minus to ground, and then label it whatever value it says. So this would be plus to minus to ground, and then a value of minus 10. So that way you only have to remember one thing. Wherever it has an arrow up or down or a dot, just at that point, draw a connection from plus to minus of that point to ground. And then label it whatever the value says. This also means this. So you could draw it as a plus 10 with a minus to plus connected there. Whatever way you are like, I visually see that correctly. They mean the same thing. All right, other questions? Comments? You guys are right ready for the exam on Tuesday? Okay, so there's some problems on that unit 3 that you can go through to give more practice. I will not be here, so my office hours, unfortunately, I won't be holding those for the next couple weeks. So you'll have a sub after Tuesday. You guys liked Amy more than Jamesina, so you get to see Amy again. She's very excited to come teach you guys. So she'll go into some second order circuits, and you guys will learn how to do those. All right. Good luck, and see you when I get back.